Now we're going to get into the coding portion of the problem. To start off, we're going to be trying to make a set of data points like we did in the experiment. Start off, we're going to import a few packages. We have NumPy for some basic algorithms and functions. Help us with that. We're going to use Plotly for any kind of plotting, make our actual plot, be able to add the all of our dimensionless numbers, Sherwood, Reynolds, Schmidt. We have it set so that the graph is dark instead of white for the graph. Personal preference, may look better this way. You may think it looks better in white. And then we have the Sci5 optimize for minimize, which can be helped with the error portion of the problem. So to start, we're going to have to collect a random sample of each of our values, not the Sherwood, but the Reynolds and the Schmidt. So to do that, we're going to have a Reynolds. We're going to set that equal to, and we're going to use NumPy, a random uniform. We're going to say random but uniform distribution. We're going to have to set parameters. These were given to us, 2,000 and 35,000 for Reynolds. So 2e to the third for this boundary, and 35e to the third for the upper boundary. And then we're going to have 100 iterations, not 1,000, 100. We're going to do the same thing. Copy this. Do the same thing for the Schmidt number. Rename it to Schmidt. And then the boundaries for that one are different. 0.6 for the lower and 2.5 for the upper boundary, again with the 100 iterations. After that, we have to have the Sherwood number, which is just the given equation, equaling 0.023 times, I don't need a parentheses there, I need a 0, times our Reynolds number, which is to the power, double multiplication sign, of 0.84 times our Schmidt number to the power of 0.4. And then we're also going to randomize that result with a 10% error. So we're going to use, again, the Sherwood number, and again our NumPy random normal this time distribution, since we already have an equation for it. What do we put here? Okay. We're going to set local equal to Sherwood, and then you're going to scale it with the 10% error, giving you just 10%, 0.1 times Sherwood. We're going to run all, make sure that we're good. Takes a second. Okay. Now that we have all of our randomized data for Reynolds, Schmidt, and Sherwood numbers that you would get from repeating the experiment over and over again, we're going to look at linear regression. So with that linear regression that we just went over in the other portion of the video, we're going to see that our matrix A, we're going to set that equal to, use NumPy and then column stack to give us a our 100 like it was straight down in the discussion of the linear regression, you know, all the ones and then all the natural logs, the Reynolds, then all the natural logs of the Schmidt. So, column stack. And so for the first column, we have to use the NP1s, which just gives us a bunch of ones, and then like, which gives us the same amount as the rest, the 100 iterations. And then we're going to use NP log for the natural log of Reynolds. Forgot to capitalize that. And then we're going to use the NP or NumPy log of the Schmidt. And we're going to wait to run that. And then like we did in the linear regression, that's our A. We have to transpose, find the symmetric matrix, find the inverse. So we're going to use that. We're going to call that B since we called the first one A. No, we called it U. So I'll go back and call it U. So our U1 ended up being the linear, the inverse. We use that to do inverse portion of the matrix. And then that was, again, times the, got rid of that. So it was the transpose, which the transpose. So we're going to do the transpose multiplied matrix X, multiply that by, not X, we're doing A. A transpose the NumPy natural log of the Sherwood. Yeah. Now, giving us what we went over for U, which is our natural log A and B and C variables that we did in the other portion, we're going to give back our U to see its values. Oop. Oh, forgot to call the like ones Reynolds. Run that again. Oops, still doesn't like it. NP column underscore stack. Okay, now you can see that we approximately have the same answers to the last two, but the first one is wrong. Now, if we go back and think about it, that's because we had 1 and not the natural log of something in our first value. So we need to raise that to an exponent, and I'm just going to do that by printing this again, giving us the U so we can see it, and then we're going to take the first, we're going to take that to the first, NumPy exponent of U and the array's first value, which is 0. Makes sense. Yeah, that works out. That's about the first value. And so that's the best way to do linear regression, to find approximate values through repetitive experiment. In this case, we just kind of faked our data, but we just, not being able to collect the data ourselves, we ran through the code to give us 100 iterations so we can simulate finding that data. Looking at minimizing the sum square error through the Penrose inverse or Penrose pseudo inverse, we have to define the sum square error to begin with, and then give it a variable to hold. I'm going to use n. Be anything, just wouldn't use anything you've already used. A, U, Reynolds, Schmidt, Sherwood. And then we're going to want to return the sum, or the NumPy sum. And we're going to use the Sherwood minus the other side of the equation, the first portion of the array, just the A value, n times the Reynolds, space that evenly, the Reynolds to the power of the second part of the second spot in the array, and then the Schmidt times, not A, you just want to use n the whole time, Schmidt times the third part of the array, and then we're going to square that sum and then square the error, and then we're going to want to minimize from sci-fi that error so it's not anything too bad. We're going to minimize our sum square error, and then we're going to use our original data points to do that. There is 0.023, 0.84, and 0.4. Oops. Index 3 is out of bounds. Oop, 3. I put in 3 for the third one, but it's just the second one being the third one. And you can see that gives us values within range of our initial values, just as the other portion did. Now we're going to look at the graphing.